Hi guys, make sure you're comfortable and ready to pause and think. Make sure you have pen and paper or something to write on, as we're going to start talking about IV characteristics, which will continue in class on Friday. Alright, so the learning objectives for this module is to identify the utility of IV curves in circuit analysis, and given one of the three sub-circuit descriptions, whether it's an IV equation, IV line, diagram of the circuit, you should be able to find the other two. Note that the circuit diagram, as you will learn, is not going to be unique. We also hope that you will learn to quickly identify IV representations of voltage sources, current sources, resistors, and combinations of the above. You will also learn to analyze whether at a given point on the IV curve, whether the subcircuit is sinking power or sourcing power. And finally, you will learn to find the operating point when you connect a couple of subcircuits. Not all of this you will learn from this video, but hopefully by the end of Friday you'll be comfortable with all of these concepts. Okay, so let's consider a circuit. It's some sort of a circuit in a box. We don't know what it is, and it has two leads. And we can fully describe the DC behavior of this circuit, that is not changing in time behavior. We can fully describe it by relating the voltage across the two terminals to the current that goes into one terminal and comes out the other. Right? So we could actually measure something like this, and you'll be doing this in the lab at some point. We could connect a voltage source that's variable and measure the current drawn by out of that voltage source, and you can study the IV relationship that way. So you can pause and think a little bit about the diagram. What you need to remember is the current meter has no voltage falling across it. It's magical. It just measures the current coming out of the voltage source. Alright, like I mentioned above, you cannot really use that to measure the voltage, an ideal voltage source, but there's an alternative measurement. You could use a current source, as you can see here, and measure the voltage across the current source to find the IV characteristics that way. Of course, good luck finding a current source. Well, we do have those, but they're not quite as frequently found as the voltage sources. There is another alternative, sometimes called the load line analysis, and that's where you connect a variable resistor across the terminals, and then you can measure the voltage across that resistor and the current that goes through that resistor, and you can characterize the circuit that way. It's not going to work very well if the circuit doesn't have any sources, because you won't really see anything. Alright, notice that just like there is no voltage drop across the current meter, there is no current going into an ideal voltmeter. So you can think about that a little bit. Alright, so we're not going to prove it, but any combination of currents or voltage sources along with resistor networks has a linear IV. It's a line on the IV curve, as you will see. And that's true no matter which two nodes you consider. So we could consider these two nodes going across the 4 ohm resistor, or we could consider going across the 2 ohm resistor. Now, those two lines are going to be different, but they're going to be lines nevertheless. Alright, why do we care about this stuff, and how do we find those IV curves? So we'll talk about that. Alright, first of all, why we care. IV curves can allow easy calculation of I and V, the operating point, when two subcircuits are connected together. Also, it can allow creating a simpler model for a given subcircuit, or if you don't know anything about the subcircuit, you can measure it and create a simple model. And those are going to be called Thevenin and Norton equivalents, and we will talk more about it on Monday. This kind of analysis will help you understand nonlinear devices later, because some regions of nonlinear devices can pretty much behave fairly linear, and then you can model them as sources and resistors. All right, so how do we find those IV lines, given that we're looking at linear circuits right now? We can use the node method that we just recently talked about for variable voltage source, and you'll see that in a second here. You can also, since it's a line and it's defined by 2 points, you can just find the intercepts of that line, which would be the open and short behavior of the subcircuit. And you can use either open or short and use equivalent resistance ideas to find the IV lines. And we'll talk more about that on Monday, because that ties in with the Thevenin and Norton equivalent circuits. All right, so let's consider a fairly simple example with a voltage source and a resistor, and let's look at it. Using the node method. All right, so imagine we connected the voltage source shown here in red, and notice that the way we define the direction of the current is that it's in SRS with respect to the circuit we're analyzing. So the first step of the node method is we add a ground, and then we can write an equation for I. As you can see, start voltage minus stop voltage across the 2 kilo ohm resistor divided by 2, and that equals I. Of course, I here is in milliamps since the resistance is in kilo ohms. All right, so we can rearrange this equation a little bit, and we can find our IV equation. I equals 1/2 V minus 3, where again I is in milliamps and V is in volts. All right, so we're done here. Okay, let's use a different method. Let's use the intercepts method. All right, so first we draw the IV axes, and then we think about it this way. Well, if the circuit is open like this, like it's shown right now, there's going to be no current flowing across the 2 kilo ohm resistor, right? It's just an open circuit, so no current can flow. We didn't complete the loop. Therefore, there's going to be a voltage across the terminals that's just equivalent to the voltage source, 6 volts. Why? Because there is no voltage drop across the resistor. So our V is just 6 volts in this case. Now let's consider if we short the circuit, then the V is 0 as opposed to I. And we can very quickly analyze this circuit and realize that I, in this case, is minus 3 milliamperes, right? The opposite of I, the opposite direction would be start voltage of 6 minus 0 divided by 2 kilo ohms, and that would be 3 milliamps. So reverse in the direction would be minus 3 milliamps. All right, so we can put these two intercepts on the axis here and draw a line through them. So you can pause here to think a little bit about that. All right, we can combine the two results that we found, and we realize that this equation, I equals 1/2 V minus 3, and the graph represent the same thing, and the circuit. All right, so what else can we figure out about it? If you remember, with the definition of SRS, and this is SRS consistent labeling for the subcircuit of the current and the voltage, when we calculate the product, which is I times V, if it's less than 0, it means it's a source, right? So if V here for this circuit is somewhere between 0 volts and 6 volts, this circuit is going to act as a power source. And you can think about it for a second here. All right, so if we apply the voltage to this subcircuit that's bigger than 6 volts, you can imagine that we're gonna end up sort of charging that 6 volt source all the way on the left, right? And therefore it's gonna be a power sink. It's a little bit trickier to think what happens when voltage is negative. When voltage is negative, both the new voltage on the right and the voltage on the left are going to be contributing to the current flowing across the 2 kilo ohms in the same direction. Right? So why is our subcircuit then a sink? And you can think about that for a second. All right, so if you're coming back, you'll realize maybe that the 6 volt source on the left is actually sourcing power, but more power is being sunk by the 2 kilo ohm resistor. Right? So the net effect of the 2 kilo ohm resistor and the 6 volt voltage source is that together they sink power. PSRS is going to be positive. That's what's happening in this newly shown quadrant where voltage is below 0. Alright, so you can think about that, and now I think you're ready to try slightly more complicated examples, and this is where we're going to pick up next time. And here's another example, and you can use either a node method or this open and short intercept to find the IV characteristics of this circuit. Alright, so try it on paper and be ready with it in lecture. And by the way, here's another one. Alright, so here's another one. This time we'll have a current source. Current source right now is a little bit of an abstraction. We understand voltage source as a battery, but what is a current source? And various things can behave like current sources, where you can buy a current source, which is going to be like a box, useful, for example, for driving lasers. Anyhow, it's easy to draw a current source on paper, and why don't you analyze this circuit and find its IV characteristics and compare to the previously analyzed circuits above. Alright, that's where we'll pick up. Thank you.